to continue our conversation about end behavior. So if you would do me a favor and go ahead and turn to your end behavior notes where it gives you this slide that says warm-up review. I'm going to give you two functions here. We're going to look at f of x being 3x squared minus 4x plus 8 all over x minus 7. And we're going to look at f of x being negative 5x to the fifth minus 4x cubed all over 2x plus 7x to the fourth. And what I'd like you to do is take a minute and pause the video and come up based on our conversation, specifically regarding the last example that we did, and give me the end behavior in limit notation for these two functions. Okay, hopefully what you remember from Tuesday is that my fastest technique to finding the end behavior of a rational function, where I have a polynomial over a polynomial, in this case a quadratic over a linear, is to take my leading terms, 3x squared in this case, over x. That simplifies to be 3x. And then hopefully thinking through our concepts from Tuesday, we remember that when I'm thinking about end behavior, it's with the idea of what is happening in the long run. So if I stick a huge number in for x, my number, the bigger I substitute, becomes bigger and bigger. So as x approaches infinity, f of x approaches infinity as well. Now, these are going to be two unique end behaviors, meaning in either direction they do something different. So as I substitute in here into this, essentially this simplified end behavior, then I can use that to gauge what my end behavior will be in the direction, in this case, of negative infinity. So if I stick in a really huge negative number, 3 times a really huge negative number is a really huge negative number. Down below here in green, my highest term on top is negative 5x to the fifth, and on bottom here is 7x to the fourth. When this simplifies, I get negative 5/7 x. Then, as I consider the end behavior, what's happening in the long run, I'm going to think about plugging in a really huge number. Well, if I'm approaching infinity, a negative times a really huge number will become negative infinity. And as I stick in a really huge negative number, a negative times a negative is a really huge positive number. I want us to go ahead and add a third example here to this slide before we turn the page. I want to look at this function. Let's list x to the fourth minus 3x plus 1 all over x squared plus 2x minus 4. Take a quick minute, hit pause on this, if you would, and consider why this one is different. Go. Okay, so in this case, when I take my leading terms, I have x to the fourth over x squared. I get x squared. The difference here is that no matter what I stick in, if I stick in a positive infinity, I get infinity. If I stick in a negative infinity, if I stick in a really large negative number and square it, it also will become really huge and positive. So we're going to think about that over the next couple days here as we progress through rational functions, because obviously this end behavior, it has a different pattern than the previous two. So we're going to hone in specifically today on that first example. So go ahead and flip the page. We're going to hone in on f of x equals 3x squared minus 4x plus 8 all over x minus 7. And we're going to think for a minute about options were in terms of finding end behavior as of Tuesday. We just used the leading terms perspective because that's quick and easy and consistent. But I want to point this out because this is going to be huge later on. We also talked about our long division and how our long division, if you remember on the very first example, we looked at how long division gave us the horizontal asymptote of 2. Well, this long end behavior, the one we just looked at, was not specific. It was infinity or negative infinity, and yet our long division can make it more specific. So if we do this long division, I'm going to remind you, x goes into 3x squared 3x times. I then multiply this out. This is 3x squared minus 21x. I subtract this line, so this becomes negative. This becomes positive. This becomes 17x. I drop down the plus 8. X goes into 17x 17 times. I then multiply through. I'm left with 17x minus 119. If you remember, this becomes negative. This becomes positive. I'm left with 127. This number right here is, or the power on x here, which is technically 0, is less than the power of my divisor. So technically this is my remainder. So hang on that for a minute. Notice that our actual answer to the division is 3x plus 17. Now I want you to take a minute and go ahead and I want us to graph in our calculators 3x squared minus 4x plus 8 all over x minus 7. And I want you to take a minute and I want you to play around with your calculator. Hit pause on your machine on the video long enough to get this picture. Now, for most of you, you're going to just get this portion. So for now, I want to help you, and I'm going to tell you what to use for your window. You should actually get these two pieces. So go ahead and put in 3x squared minus 4x plus 8. And then notice that if you can just click on these, on the x-axis values on either end, you can actually put in an endpoint here and an endpoint here. Here and here as well. And you can just estimate. Originally I put in negative 50 here. And this is just so that in your calculator, even though you wouldn't know how to do this right now without guidance, eventually you will. And here I can put in negative 100. Up here I can put in 125. And I've got a pretty good picture this way. But what I want you to notice is if I were to take my hand and cover up the middle, I would cover up this section because we don't yet know what's happening here. Some of you might be able to say, oh yeah, that's a vertical asymptote there. If you kind of see this, if you're getting somewhat decent at this, just from our quick conversations, you might notice, oh, well look, there's a vertical asymptote at 7. But you really don't know how to get this side or this side. All we know is we've got two pieces, and the only reason we know that is from the graph. But what we also know now is that it looks like our end behavior takes on the pattern of 3x plus 17. So I want you to take a second and give yourself a new function. And when you're ready, hit enter. And what you should notice is a really cool feature. While we have behavior happening in the middle, it is undoubtedly obvious that my blue graph, my original rational function, is approaching my line in either direction. So I want you to take a minute. I just want you to put a sketch. It doesn't have to be perfect, but take a minute and transfer that to the graph. Now notice, again, this is just a quick sketch, so don't stress too much about it, but I have a y-intercept of 17. Now let's say I did these by tens. I would have somewhere in here of a 17. I'd go up 3 over 1. I'm going to have this asymptote. Now, again, let me stress, we're not worried too much right now about the perfectness of the middle of the graph. And yet we can get this inside portion and this outside portion. And though we don't know exactly where it stops and comes down or where this goes like this, we don't know all those details. It's not a perfect graph. We should fix it a little bit here. I do know I have this vertical asymptote. I know that this is happening up in here. The key today is not inherently to know how to get the middle. I don't need you to know that today. But what I do want you to notice is that this blue graph is approaching that green line. And this blue graph is approaching the green line in this direction. My end behavior asymptote is a diagonal line. My end behavior is not a horizontal asymptote. It is a diagonal or oblique asymptote. We're going to write it like this, at y equals 3x plus 17. So leading up to today, we just had horizontal asymptotes. Now we have oblique or diagonal asymptotes. On the next slide, we really don't inherently need that graph. But what I want you to have room for, and I'm just going to scoot this over, and we're just going to fill out here on the side, is I want to remind you of something else. That is the process of synthetic division. If I gave you 3x squared minus 4x plus 8 all over x minus 7, because, now listen carefully, this is a linear divisor with a coefficient of 1. I can take my coefficients. I can put whatever would make this 0 in that little box. I can drop the 3, and I can multiply. And very quickly, without nearly having to deal with my long division, I now have the coefficients of my remaining terms. Remember, this is 1 power lower than the 3x squared up here. This is then in decreasing order. This is 3x to the first plus 17. If you don't remember that, I'm going to encourage you to get to MathLab, or you can even Google it if you want to, because that's taught to you in Algebra 2, as is long division. I also want to remind you this works. Add this for me. You can use synthetic division in this case when the divisor is linear. Now, if you are dividing by a quadratic, dividing by a cubic, then you have to use long division. If you want to, hit pause and add that to your notes. But I can use synthetic division when the divisor is linear, and good heavens, it makes life easier. On the next slide, it's the last slide we're going to do in these notes. I want to officially add this definition. An oblique, or also called a slant asymptote, is a diagonal line in the form y equals mx plus b, which the graph of the function approaches when x approaches positive or negative infinity. It is, like the other horizontal asymptote, an end behavior asymptote. And if you flip back to our notes, you should have written down this phrase. It is not a restriction. That's going to really matter in the next couple days, especially next week. It is not a restriction. So, I'm going to give you 2 more really quickly that I'd like you to do to find the oblique asymptote. But I'm going to say this. You can use long division for these directions or synthetic, whichever is legal. So, the 2 that you're going to do are, number 1, f of x equals 2x cubed minus 3x squared plus 9 all over x squared plus 8x minus 4. And this one, f of x equals 3x squared minus 2x plus 1 all over x minus 8. Hit pause. Go ahead and find those oblique asymptotes. Okay, so the last thing we're going to do is just crank through these. Notice this is a cubic divided by a quadratic. Since this divisor is not linear, I have to use long division. I've got 2x cubed minus 3x squared. I put a placeholder, plus 9. I've got x squared plus 8x minus 4. X squared goes into 2x cubed 2x times. I'm left with 2x cubed plus 16x squared minus 8x. Reminder, you then subtract the entire line. This subtracts, this adds. These are gone. I'm left with negative 19x squared plus 8x plus 9. X squared goes into that number minus 19 times. This is negative 19x squared. Then you've got to do negative 19 times 8, which is 152, so minus 152x. Then 19 times 4 is 76, so this is a positive 76. And then I want to point this out. We can talk more about this tomorrow or Monday. But when I subtract this whole line, this becomes positive, this becomes positive, this becomes negative. These are gone. Anything that is less than a power of 2 is a remainder. So this 160x here plus 85 is tacked on here, but this section, per our conversation yesterday, will go towards 0. So my end behavior asymptote is y equals 2x minus 19. Now, just a quick comment. If I needed to then give the limit notation of that end behavior, I still think of it the same way. 2 times a huge number minus 19 is still huge. And similarly, 2 times a huge negative number minus 19 is still hugely negative. I'm sure that's not a word. And then, I'll just comment on this in case this stressed you out at all. If the idea of why this remainder goes towards 0 is a little stressful, we'll talk about it more tomorrow or Monday. And then quickly on the last one, here I am, let me put a divider here, I am dividing by a linear factor. I can put 8 here as whatever makes this 0. This will be 3, negative 2, 1. I would have to put a placeholder if it was missing a variable there with a coefficient of 0. Drop the 3. This is 24. This is 22. And this is some remainder that I really don't care about. So it's 176, don't care. This is 3x plus 22. So my end behavior asymptote is there. In this case, my limit notation, similar to this last one, would be the exact same. The same as this. With that in mind, your assignment is on the back. It is due on Monday. It is part B. You're going to use long or synthetic division to find the end behavior asymptote. You're going to circle your equation for the asymptote and describe what type of asymptote it is. On the bottom 3, those are going to be a little different. So the first 3 are going to feel just the same. The bottom 3 are going to feel a little more challenging. I want you to think through what would the picture be of those asymptotes. We'll talk about that on Monday. I also want to comment, there should be something starting to click in your head. And I'll leave you with this. Under what situations would we have a horizontal asymptote where I get a specific number that's not 0? And we'll start class tomorrow with this before you have your workday. Under what conditions would I have a horizontal asymptote that is 0? And under what conditions would I have an oblique or slant or diagonal asymptote? What kind of P of x over Q of x would cause each? What rational function would cause this scenario, that scenario, and that scenario? That is where we will start tomorrow. We'll whip through that, and then the rest of the time will be yours to work. Hope you have an awesome Thursday.